Okay, we're going to evaluate some basic logs using the changing between forms. So, log 1000. It asks a question, and you got to know the question it asks. When you look at these things, remember, it's asking about an exponent. What power do you raise 10 to? Why 10? Because remember, that's the base here, right? 10 right down there. Because if it's not there, it's 10. What power do you raise 10 to get 1000? So sometimes it's helpful to add the equal sign and put an unknown. Put an x, y, b, r, I don't care what you put out there. Usually I just put an x out there, right? So then it's 10 to the x. So I rewrite it. 10 to this power equals 1000. So what is that? What power is that? 3, right? So this equals 3. 10 to the third power is 1000. Okay? Now you can see that on the calculator, because remember your calculator has base 10. So if I go on the calculator, turn it on here, and I go, okay, log of 1000. So here's your log key, right? Log, that's base 10, right? Of 1000. 1, 0, 0, 0. You can put the parentheses at the end and hit enter. 3. So it'll do base 10. Only base 10 though. Okay? Let's look at our next example. Log base 2 of 32. So remember here, it's asking a question again. 2 raised to what power, this unknown, is equal to 32? 2 raised to this power is equal to 32. Well, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th, right, is 32. So it's log base 2 of 32 is actually equal to 5. 2 to the 5th is 32. And we can't check that one on the calculator because it doesn't work. The calculator only does base 10 and base e. Okay? Let's do another one here. Natural log of 4. Well, put a little equals an unknown. What's the base? Natural log is e. So e to the x, it's saying, is equal to 4. Oh, what power do I raise e to get 4? I don't know, because e is some messed up decimal, right? So I need a calculator for this one. I can't do it, or I can do it by estimation. But if we just grab the calculator, I just take natural log of 4 on there. So I go natural log of 4, 1.3862, so 1.39. So this is approximately, we'll say that x is approximately equal to 1.39, right? Yep, 1.39. Otherwise, you can say natural log of 4 is approximately equal to 1.39 rounded off to 2 decimal places. All right, what about log of 25? Well, same kind of idea, right? There's a 10 there. 10 raised to the x is equal to 25. Well, 10 to the first is 10. 10 squared is 100, so it's really close to 1. 1.2 or something. Again, take the calculator. Log 25. Oh, 1.4. 1.4. So log of base 10 of 25 is about 1.4. You better put squiggly lines because that means approximately equal to. Alright, let's have you try to evaluate a few here. See if you can do these ones. Log 1, 4 times, that's what that means, 4 times log base 3 of 27, and natural log e to the 10. So I'll give you a second, pause it here, and see if you can do those. Okay, we don't need a calculator for this. Don't grab the calculator just because it's base 10. Think about it first. Log base 10 of 1. What's it equal to? 10 to the x equals 1. Well, 10 to what power equals 1? 0. So in this case, x is 0, so this thing equals 0. Log of 1 is 0. And that's the same for any, right? If this was a base 6, would it matter? 6 to the 0 power is 1. Remember changing it? So the base doesn't matter. Okay? When you have 1 put in there, you're always going to get 0 out. Alright, this one. The 4 says 4 times this. That's what that means on the outside. So we'll evaluate the order of operations first. So let's do the log base 3 of 27 first. Alright, so if I take that out and go like this, I'm going to do that first. Set it equal to an unknown. 3 to the x equals 27, right? 3 to the x equals 27, so you're changing it. that means 3 must be, or x must be a 3. Alright? So that means this equals, this portion right here in yellow is 3, like that. And then it says 4 times 3 is 12. So the whole thing together equals 12. Okay, over here, this says the natural log of e to the 10th. Remember, the base is e, set equal to this, and watch, the base e down here to this x, right, changing it to exponential, has to equal, right, this to this equals the inside here, e to the 10th. Well, it looks complicated, but obviously, right, x has to be 10 in this case. So when you have the natural log of e to the 10th, and the base down here matches this, it has to just be the 10, right? Okay, hope that helped evaluate some of the simple log functions. Let's look at one other property before we end here. Let's look at the inverse properties, because they also help us evaluate some log functions here. Now the two properties we want to look at, because log is an inverse, you have b raised to the log of b, x equals x, and log base b of b to the x equals x. We just looked at this one. We just kind of saw how that worked, where they match up and you just get the exponent out, right? Well, how these are true is they're based on the inverse properties between the exponential and log. Since they're inverses, statements like this are true from the inverse chapter. If you have the f of x and you put, let's see, let me change that around here if I want to start like this. If you have f of f inverse like this, you're supposed to, this input x goes in, produces a y, the y goes into this guy and then produces an x. You're supposed to get the x back out. And if you do it the other way, the same kind of idea, like this, put function f inside f inverse, you're supposed to get x back out. And so that's what I'm showing you here, okay? Their relationship, because remember they're swapped. Here's function f of x is b to the x. Its inverse is the log function. Okay, that's its inverse. So if I take f of f inverse, that's f of log base b to the x, right? That goes into the exponential function. Well, remember, in here is in here. So that's where the b to the log base b of x comes from, right there. The b to the log base b of x, because that's the input, and that has to equal x. That has to equal x because they're inverses of each other. The next one, if we take f inverse of f of x, so we're doing this one, f of x is b to the x. Now this input is going in here, which is in this right here. That's where this one's coming from. The b to the x replaces the x. Log base b of b to the x. But that whole thing has to equal x as well, see? So f of x going into here produces x out. They're a little complicated, but basically if you can remember these two rules here, which they kind of make sense. This one's kind of hard to get up, but you just kind of remember it. The bases equal each other, it's just the input right there, x. If these bases equal each other, it's the exponent. This one usually makes sense. This one you'll definitely see like this. Look at this example. 5 raised to the log base 5 of x plus 8. Well, you're like, what do you do here? Well, the base and the base are the same, so you're just going to get what the input is, and the input is this mess here, so you get x plus 8. That's what it equals. That's according to the first rule right here. Alright, then this one makes sense though, see? 4 raised to what power is 4 to the 3 plus x? Well, according to the next one, if the bases are the same, which 4 and 4 are, then you just get the exponent, 3 plus x, or whatever's up here, right? Whatever's up in the exponent. But that makes sense, and this one you can kind of see it. So those are the inverse properties. If you see those in the homework, just write down the answer.